Today we want to go through the process of potential energy surface fitting using our monomial symmetrization program MSA. Here we use the hydrogen-water interaction as an example to go through the entire process of the potential fitting. We highly recommend that you follow the exact procedure once and get familiar with our program. Before using our program to fit the potential energy surface, we need to determine the permutational symmetry group we would like to use. Usually it is the same as the molecular formula of our testing structure, but sometimes the reduced symmetry group could be used. In our hydrogen-water example, the full symmetry group is 4,1 because the molecular formula of this structure is A4B. But we don't expect any hydrogen exchange between hydrogen and water, so the symmetry group of A2B2C is also reasonable. In this video, we will use 2:1. Right now, we're inside a package called MSA. Inside the package, we have a list of files and folders. In this package, we have a folder called SRC that contains source codes. Inside this folder, there are two Perl scripts, post.emsa.pl and derivative.pl, a test program getPot.f90, and a test data file, test.xyz. A file contains expected output of the test, expected.out, a makefile that compiles the test program, and a folder called EMSA. The makefile here uses iFort compiler, and also the MKL library for the DDL subroutine. We may need to modify this file, depending on the linear algebra package and different compilers and operating systems. Inside EMSA folder, we have the main codes of MSA written in C++, and another makefile that is used to compile these codes. We use G++ for compiling C++, and again, we may need to modify the makefile if other compilers are used. Now we go back to the main directory. In addition to the SRC folder, here we also have two scripts written in Python called msa.py and reset. The msa.py is the one we would run for the fitting, but the reset file deletes all the outputs and results generated by this fitting program, and we need to be careful about this script. In the main directory, there is also a readme.txt file with documentations and procedures of the fitting in it. There is a dataset used for the fitting points.data as well. In this example, the data file contains geometries and hydrogen-water dimer, and corresponding interaction energies. For each geometry, the first line shows the number of atoms, and the second line shows the interaction energy in Hartree. The following lines are just Cartesian coordinates of the molecule in angstrom. The way we put in the order of the atoms has to be consistent with their formula. We use A2B2C symmetry in this example, so we put coordinates of A first, then B, and then C. Suppose we have already modified the two makefiles. We just run the Python script msa.py, like we do on the screen. Or here we can type in python msa.py. We first put in the maximum polynomial order of the fit. In our example, we use 4. This is smaller than the typical values we use in real applications, but it runs fast as a demonstration. The computational cost increases dramatically, so we suggest that you start with lower order. Then we put in the symmetry group. As we said, we use 2:1. Finally, we put in the name of the data file, which is points.data. Now the program tells us the number of coefficients and the number of points in the data file on the screen, and the program asks if we would like to continue. If the number of coefficients is too small, it may lead to large fitting error. Or if it's too large, the computational cost is high and it may also cause overfitting. We can enter N to terminate and then pick another order. Here, we just enter Y and continue. The program then prints some instructions about weighting on the screen. We assign larger weights for points with lower energy, so that fit is more accurate near the minimum. In this demonstration, we simply enter N. Then the program fits the potential energy surface, and when it finishes, the root mean square fitting error is printed on the screen. The coefficients of the fit are written in the file called coefficient.data. And 4 Fortran code files, basis.f90, getPot.f90, gradient.f90, and petshell.f90 are generated. The basis.f90 and gradient.f90 defines the fitting basis of their first derivative. The petshell.f90 is the interface to use the fitted potential. Inside the petshell.f90, the pet's initial subroutine is used to initialize the fitted potential, that is, to read in the coefficients. The function f in the file is used to calculate the potential, and its input x, y, z are the Cartesian coordinates in unit bore. Function g in pet's fitting.f90 is used to calculate the gradient, and the input x, y, z are also the Cartesian coordinates in unit bore. The test program getPot.f90 is an example that shows how to use the fitted potential. The coefficient.data, basis.f90, gradient.f90, and petshell.f90 should be in the same folder as this getPot.f90 main program. And in the Fortran code of this main program, we have used petshell in the first line. And subroutine pet's initial is called at the beginning to read in the coefficients of the fitted potential. After that, we can use the function f and g to calculate the potential energy and the gradient of an arbitrary geometry. The test program getPot.x is automatically compiled, and we run this test program as the following. The results are written in test.out, and they should be the same as those in the expected.out file. Now we have successfully gone through the whole process to fit the potential energy surface using the MSA software.